Go ahead.
Hello, everyone. Thank you for participating in today's seminar session. It's my honor to introduce Dr. David Bradwell to you. Dr. Bradwell received his PhD and Master of Engineering in Materials Science and Engineering from Massachusetts Institute of Technology. Also, he received his bachelor degree in Engineering Physics from Queen's University. Dr. Bradwell is Chief Technology Officer and co-founder of Embry, a spin-out company from MIT. In 2010, he received a TR35 award for being a top innovator under 35 from Technology Review magazine. Dr. Bradwell develops and commercializes the liquid metal battery technology with a focus on creating a low-cost, safe, and long lifespan storage technology for grid-scale energy storage applications. He has a wide array of company functions since its founding, including product road mapping, budgeting, fundraising, team building, cell development, systems engineering, manufacturing, HR, EHS, and facility and IP. Presently, he is part of Embry's executive leadership team focused on cell development and applied research. The company has raised over $200 million in funding, including funding from Bill Gates, Reliance New Energy Solar, Paulson & Co., and others. In today's seminar session, his talk is about calcium antimony liquid metal batteries for grid-scale energy storage application. Dr. Bradwell, it's our pleasure to have you in today's seminar session. Please start and go.
Great. Well, thank you very much. And thank you for coming today. And thank you for those that are online as well. I'll probably do a bit of back and forth between the video and the audience here. So let me just switch over to my slides. All right, so it is a pleasure to be here today. This is my first talk since the pandemic hit. So it's, hopefully it's not a rusty performance, but really excited to be here and share my story. I've been working on this project for well over a decade with my master's PhD thesis and leading the company's a lot of technology development at the company for about 10 years. So excited to share the story with you and happy to answer questions and hear from you guys as well. So we are developing at Embry a calcium and antimony liquid metal battery for grid scale stationary energy storage applications. And this is the work that was based on my master's and PhD thesis work at MIT, and spun it into a company and are working to move it out into the real world. So just a quick high-level summary of kind of what we're doing at our company. We are developing these low-cost batteries for grid-scale stationary energy storage applications, targeting 30 to 50% lower cost than existing lithium-ion systems, which are the dominant form of batteries in the energy storage market that are being deployed. This technology promises to be longer life. That's based on the fundamental mechanisms of how the battery operates, how it charges and discharges, the electrode materials, as well as being a safer technology than existing lithium-ion systems. Our path to commercialize this technology will be to build these systems, and like what you're seeing on the bottom right of the screen here, and selling these directly to utilities or independent power providers for this application. And we are building, not just doing the science and the research, but building cells, building manufacturing equipment to build those cells, building the systems, building the high volume facilities to build and operate facilities to build these DC systems, which will be deployed starting this year, expanding next year, and then high volume production in 2024. Bit of a background on the technology. Is everything all right?
Yes.
Just 1 second.
There you go.
Okay. Sorry for anyone online if that wasn't shared properly. So the work spun out of MIT in 2010. We have gotten great investors, as was mentioned earlier, and recently closed a $144 million funding round, which was fantastic and has allowed us to expand our team, expand our facility, and accelerate our development. So the first thing that I'd like to start with is why? Why are we doing this? Why are we working on this problem? And the why we're doing it is that there's a huge need for energy storage on the grid. Today's electricity grid has very little storage. It's been described as the world's largest supply chain with no warehouses. The energy powering the lights in this room is being generated this very instant somewhere else on the grid and being transmitted through transmission lines, through distribution facilities, systems, and then being delivered here. And that's worked okay with conventional generators, with natural gas turbines and nuclear plants and coal plants. And so because those facilities, those plants can ramp production up and down to meet the varying demand that happens throughout the day. And this is a graph showing the production or the demand for electricity in New England last week. This is publicly accessible data through ISO New England's website. Interestingly, at this time of the year, there's actually a double peak. There's a peak in the morning, and when people leave for work, there's a peak in the afternoon when they come home. And the challenge is coupling this with the supply that we're looking to do. With wind and solar power being very intermittent, unreliable. And so energy storage is really the key to matching intermittent supply. And it's like amazing what has happened in this space. When I started working on this more than a decade ago now, there were not systems like this out there. These are massive facilities going in around the world. Each square in this PV array that's deployed in California is larger than a football field. So this is miles across in each direction. And then now reaching 2 cents a kilowatt hour project costs, which is some of the best, some of the lowest cost electricity, new forms of electricity generation you can get, compared to say 15 cents a kilowatt hour that you're probably paying at home or something in that range. So, amazing trends in the marketplace, and the prices have come down enormously. This is a graph showing, 82% drop in the cost of solar photovoltaics over the last 10 years, and similar cost drops in concentrated solar, and as well as wind. And so we're at the point now where, as you can see in the bottom right graph here, that we're now getting to systems that are deployed at lower cost than conventional generators like fossil fuel generation. And then that's when we expect these systems to get deployed even more quickly, and that's when storage becomes even more important. One question is, what type of storage is needed to support this future grid? And there was an interesting study done in June of 2020 in the Midwest region of the US, looking at different types of storage, what the attributes of storage was needed to allow for large-scale penetration of intermittent renewables like wind and solar. This study found that you could get to 95 to 100% of your grid powered from renewables with storage with daily cycling applications. Daily cycling capability, so 4 to 12 hours. And that got to a place where the cost of that electricity was competitive. We are hearing a lot of feedback through the audio. So if you're online and can mute yourself, that would be great until you have questions. Thanks. All right. And any questions so far on this? Is this all making sense? Sure.
I guess one of the other things that I was kind of curious about is, did this study consider the fact? So one of the things that, going forward with the grid, like you said, storage is a big deal. But there's two pieces to the storage. There's the utility version of storage, which is where your company is focused, and then there's the consumer end storage, which it doesn't seem like you guys are as focused on that. However, there's some information that I've seen about that, which is saying that as electrification becomes more commonplace for everyday people, everyday houses, more houses will have batteries. And as a result, grid storage will become slightly less necessary over time as the number of batteries just sitting around in houses, large scale batteries sitting around in houses increase. Then it becomes a complicated dynamic of trying to reroute power on the grid between those sources.
Yeah.
But do you guys have any plans to kind of move your system from both just a grid targeted storage application to in-home targeted application?
Yes. So in case that audio didn't come through into the video, so the question was whether or not our batteries were going to be, whether we were going to target our batteries for at home, the distributed generation or storage. Short answer is no, not really, not at the home level. Partly due to the fact that our batteries need to be big for thermal reasons. But I also think there's a very strong argument that it's not the best cost-effective solution, that it's expensive to deploy a lot of small systems compared to massive. That's why you're seeing in PV, the lowest cost systems are the largest systems, and massive large-scale energy storage systems are going in around the world. And that's the most cost-effective path to enable renewables on the grid. And so speaking to the market a little bit, as the folks have projected out what the market is for different types of technologies and different types of storage technologies for different applications, the lion's share of it is in this 4+ hours, generally 4 to 12-hour discharge duration application for these different areas: distribution support, transmission support, energy shifting, peak capacity, peaking capacity, and that gets you to tens of gigawatt hours per year volumes. And this market is exploding. We're responding to requests for proposals for projects that are gigawatt hours in scale, and that would have been unimaginable 5 years ago. So shifting to talk a little bit about our technology and our approach. So this all was inspired by my professor back at MIT, Professor Don Sadoway, who had worked in non-aqueous electrochemistry, molten salt electrochemistry, specifically focusing on electrolytic production of metals. And one of the biggest examples of that in the industry is aluminum production of aluminum. Aluminum is produced through this kind of crazy high temperature process that operates at close to 1,000 degrees Celsius, uses molten cryolite, which is one of the world's most corrosive materials, which you can dissolve aluminum oxide, which you mine out of the ground, into, and then you pump current through it using these massive carbon electrodes and a carbon floor. And through that process, you convert the aluminum 3+ ions that come from the aluminum oxide, and you pump electrons into them, creating aluminum metal, which then deposits underneath us and pools in this big, thick layer. And this is all happening at these high temperatures and the extreme conditions. And they consume massive amounts of electricity, gigawatt hours a day in these facilities, which might be a mile long and 20, 30 meters across in these massive pot lines, as they call them. And so this idea originated from the concept of whether or not you could then use that as an inspiration to create a battery that can not only consume massive amounts of energy, but also put that energy back into the grid. That was the theory or the hypothesis. And so one place to then start is to ask, why isn't an aluminum smelter a battery? Why can't you not only put energy in, but also get the energy back out? And one of the reasons is because of the way that the cell is configured. It has as I said, a molten cryolite electrolyte, liquid aluminum pooling on the bottom. And then during this process, you not only produce aluminum, but you also produce oxygen, which reacts with the graphite anode and produces carbon dioxide and bubbles away. So that oxygen and carbon dioxide isn't there to allow for the back reaction. So we replace a gaseous component with another liquid layer. And so the original concept was a 3-liquid layer battery that could charge at extremely high power rates and current densities, and then discharge back into the grid. And that's where the liquid metal battery concept was born. So, I was involved with Professor Sadoway at this point in time and helped him to identify suitable materials for these first cells, and got into the lab, built those first cells, and we're able to get it to operate. This is one of our first batteries that we built back at MIT with a magnesium top electrode and an antimony, liquid antimony negative electrode and molten salt in between, and a little graphite crucible that's about 1 inch diameter, and charge and discharge it, and showed the viability of this general approach. So successful operation. Unfortunately, had low voltage and needed to be operated at pretty high temperature. But it was a very interesting proof of concept. And it let us get started. With that early work, we were able to attract more funding from Total and RPE, actually had $12 million go to the research group, grew that team up to 20 individuals, postdocs, graduate students, and others, and really propelled the research forward. And then throughout that process, we got some great academic publications, from JAX to Nature and others, Advanced Materials, ECS, studying different materials that had higher voltage, lower operating temperature, show the cyclability of these systems as well. And so we're able to have good academic success, which was great. But academic success alone isn't going to change the world. Writing a paper doesn't actually directly cause a change. It might precipitate it or catalyze it, but it doesn't actually have the impact. So we were focused ourselves on now moving the technology into the market, get it into the market, so it can start having a positive impact. Switching gears to our startup. So then in 2010, shortly after we received that major funding from Total and RPE, we founded Ambry. Ambry was born in the heart of Cambridge. That's where our name comes from. You drop the C, it's the next 5 letters in the town. And we were able to get funding from Bill Gates, Coastal Ventures, and Total. A bit of a funny side story. So the way that we ended up getting engaged with Bill Gates was that Bill Gates had recently retired from Microsoft. He was figuring out what he was going to do with his time. He's works incredibly hard, loves learning things. So he's learning about different areas that he could invest in, including in chemistry. My advisor at the time, Don Sadoway, and it still is a phenomenal lecturer at MIT, taught about half of the undergrads that went through MIT in Introduction to Solid State Chemistry. And that course had been put onto iTunes, put into the public sphere, allowed to be watched by anyone. And so Bill Gates was interviewed by the Seattle Times or a Seattle newspaper and was asked, what are you doing with your time now? I said, well, I'm learning about a lot of different things. And if you ever want to learn about chemistry, you should watch Don Sadoway's chemistry lecture. And so we knew that he was watching Don Sadoway, and that was exciting for us. And so several months later, maybe a year later, Don got an email and it said, Don, I'd love to come visit you. Love your teaching, and I'd love to meet with you, see what if there's any ways we can work together. Signed, Bill Gates. And he looked at that email, it's obviously a fake, and he deletes it and he ignores it. And a couple of weeks go by, and his assistant gets back to him. Don, you got to get back. Bill Gates wants to meet you. And so they ended up meeting, hitting it off, and talking about this project during that discussion. And Bill basically said, if you ever want to start a company, I'd love to help you commercialize this thing. So bit of a side story, which is kind of fun to tell. So we got some great early investors from these folks. Have a 40,000 square foot facility in Marlborough, which is where we're fully located now. And then recently raised $144 million from great new investors as well, from Reliance, Paulson and Company, and Bill Gates and others. So an exciting time for us. The ups and downs that come with a startup are always interesting. We were in fundraising mode for a few years leading up to this, and the market's changed. We make great advancements in the technology, and we're able to close a great funding round together. So after starting the company, we actually initially started commercializing a different cell chemistry, more akin to that original liquid metal battery concept. And in 2017, we were watching the markets, and the price of lithium-ion batteries came down precipitously. It was amazing. Their fall went from over $1,000 a kilowatt hour to $600, $500, $400 a kilowatt hour, and they were just projected to continue to decline. So we've been dabbling in some other cell chemistries, and at this point in time decided that we were going to pivot to a very different cell chemistry, which is based on calcium and antimony, in order to stay below future pricing of lithium-ion systems. So it was a big moment for us as a company, because it set us back from our technology readiness, needed more years of research. And we were very grateful that Bill Gates in particular was very supportive of our transition and supported us through this process. So we pivoted from this 3 liquid layer battery to a battery that had these actually vertical electrodes, get more energy stacked together into an individual cell, operate at a lower temperature. And very importantly, instead of 3 liquid components, we swapped out one of the liquid components for solid particles of antimony. And I can talk a little bit about why that was in a moment. But a big pivot for us. Now, one of the things that factored into our decision-making process when we decided to change chemistries was the scalability of those materials. And I've heard a lot of folks talk about crustal abundance of different elements and focus on that as kind of a threshold issue. For me, crystal abundance doesn't really matter. I don't really care how much of it is out there, but how much of it is actually accessible, how much are we producing, how difficult would it be to greatly expand the amount of production of those materials? And so we've instead focused on global production of the different elements. And this is a great graph from, it's a bit old now, but 2012, showing production of different elements by atomic number. I added on this dotted red line, which is an approximate value of the amount that you need in order to get to gigawatt hours of production. And so calcium is obviously widely produced. Antimony is also produced at sufficient levels to get us to tens of gigawatt hours per year of production, although it's a little more limiting, and it is an area that we're focusing on to make sure we can fully expand. But it is amazing to learn more about global supply chains and the impact that happens at different world events and local events. And so it is an area that I underappreciated as a graduate student. I would say that these things really do matter when you are trying to scale technologies. So with these materials in mind, we can project to a system that will be 30 to 50% lower cost than lithium ion, future lithium ion pricing. So I'll talk a little bit about the technology itself. I consider myself to be an electrochemist, and so I could probably talk for hours on this stuff. But the way that our battery is configured is we have a liquid calcium alloy anode, and then a positive electrode that has solid particles of antimony, and then a layer of liquid salt in between. Now, if you were just to take pure calcium and pure antimony and mix them together, they release a ton of energy. They can actually heat up to about 4,000 degrees Celsius just from the energy of that alloying reaction, which always boggles my mind because you're just putting metals together. But these metals in particular have a lot of energy stored in their potential bonds. So, but we don't want that to happen, obviously, in our battery. So we keep them separated by this layer of molten salt. And then during the discharge process, the calcium sheds electrons, turns into ions, which dissolve into the salt through this half reaction here. And then and then that electron passes through an external circuit, returns back to the positive electrode, where it recombines with calcium ions, antimony, and the electrons to create the discharge state product. Now, through that electrochemical process, you can actually extract all the energy of that chemical reaction from that electron. So the electron is carrying the energy of that chemical reaction, which you can then use to put the energy into the grid. So I find it fascinating that you can convert this chemical potential energy into electricity, to electrical power, and electrical energy through this process. Now, to charge the battery up, you simply pump electrons in the opposite direction. Electrons come back, causing the calcium to come out of the antimony into the salt and then replate and recreate that liquid electrode every time the battery is charged. So you're actually destroying and then recreating that negative electrode every time the battery operates. And that's one of the reasons the battery has very good cycle life, because the battery can, you're destroying and recreating this electrode every time. So you don't have residual particles that can have film formation or particle cracking or other mechanisms that cause typical batteries to fade and fail. This battery ultimately, projects to be low cost, long cycle life, operates at 500 degrees Celsius, through this unique electrochemical process. I should pause there. Any questions on the electrochemistry of it? Yeah.
So basically, you recreate the negative electrode each time.
That's correct. Yeah.
How many cycle life do you have?
So we've shown thousands of cycles. I think the one we have here shows 5,000 cycles. To get to a 20-year daily cycling applications, you need 7,000 cycles. It's a challenge though to show a 20-year life product, in an R&D period, right? Because you don't have 20 years to prove it out. And these batteries are going to be discharging for 4 hours at a time, charging at 4 hours. So that's 8 hours per cycle, 3 cycles a day, 100 cycles a month. So 1,000 cycles a year. So there's limits on how fast you can accelerate this testing under full depth of discharge.
Okay, so it's about 5 to 10 years of a lifespan.
We're targeting 20-year lifespan. We haven't done 20 years of operation, but yes, we expect to be a 20-year plus life battery, 7 to 10,000 cycles. Yep. Yep.
Does the high temperature and the liquid phase increase like the internal cell resistance, which might limit power density for charge and discharge speeds? So really the reverse. So high temperature lets you overcome kinetic barriers more easily. And so the reactions are extremely facile, that depositing liquid metal at these temperatures has very little overpotential. The dominant form of overpotential in our battery is the resistance of the ions through the electrolyte, which is not very high. So we're actually able to operate at hundreds of milliamps per square centimeter compared to some lithium ion batteries, which might be 5 or 1 milliamp per square centimeter. That allows us to thicken up the electrodes because we can deposit more material over a 4-hour or 8-hour period. And that's one of the reasons we can get down to lower costs, is we don't have hundreds or dozens of thin stacked electrodes. We actually have just a few bulky electrodes, which makes manufacturing simpler, and so forth. Yeah.
So where does the calcium antimony alloy, where does that actually form?
So it forms an intermetallic. It's a structured, crystalline material, and there's different phases that form over time as well. But it's an intermetallic.
And so where does it Where would it actually form? Does it form like at the interface between the electrodes and the electrolyte, or?
Yeah, so the electrode itself is actually not, this is a simplified
Right.
image, of course. So it's actually solid particles distributed in that region with salt in between it. And so you actually end up getting deposition of the calcium throughout that electrode. You do see a bit more preferential deposition and conversion closer to the front interface and then kind of progressing back in, but it does kind of all get accessed. One of the other interesting things about the chemistry is that the antimony, when it forms this intermetallic in a discharged product, you actually get 3 electrons from every atom of antimony, which is extremely high capacity. If you think about a lithium ion battery chemistry, which might be a lithium iron phosphate, lithium iron phosphorus, 4 oxygens, maybe you get half an electron out of that whole thing. And so each small antimony atom gets 3 electrons. And that's one of the reasons we actually get good energy density out of our electrode materials.
So you might have partially answered this already, but because this is oversimplified, this is a vertical cell now, but this is a vertically oriented cell, so a horizontally oriented cell. So how are you maintaining a layer of liquid electrolyte between your liquid, like the calcium chloride, between your liquid calcium and your solid antimony?
Yeah. So the cell's configured like this, as I flashed up earlier. And so the way that the cell's configured is we have these bays where the particles of antimony are placed. You can actually see kind of an actual cell positive current collector housing here. And so there are areas here where the antimony particles are loaded. The cell is filled with salt, and then the lid is placed onto the cell with the vertical negative electrodes. And so the salt's easy. Salt just floats around. The more challenging one is the calcium electrode, which is in a liquid state. And so why doesn't that just float up and rest on the top of the cell? Because it's lower density. And so and that's kind of where a lot of the IP and nuanced design is there. But metal likes to wet other metals. So there's a preferential wetting of metal onto metal compared to salt onto metal. And so as you're depositing the calcium onto this metal porous negative electrode, it's like water into a sponge. It gets sucked in and is held in place through surface tension.
Thank you.
Yeah. Yes.
Can you talk about round trip efficiency?
Yes. Actually, the next slide I think mentions it, but because of our operating temperature, fast kinetics, we're getting 80 to 90% round trip energy efficiency, which is not quite as good as lithium ion, better than lead acid, better than pumped hydro, some of the other competitors in the space, but we think very, very much good enough for this application. Yes, another question.
Do you face any difficulties with respect to your chloride-based salt in terms of
corrosion? Yeah. So the question was, have we faced any difficulties with the chloride-based salts for corrosion and things? So yeah, molten salt is very interesting because it's absolutely can be a very, very corrosive medium, including against stainless steel, which our cell is made of. Interestingly, the materials or salts only really corrosive if there's oxygen and moisture present. And so if you have an open molten salt and you dip stainless steel into it, yes, absolutely it can corrode. But our cells are fully sealed. So we actually build the cells in an inert environment, weld them shut and seal them so no air gets in. And under that condition, the cells do not show corrosion. We've had cells operate for 5+ years and the electrode materials and container materials look great. No obvious signs of corrosion. All right, so this is the cell product that we're commercializing. It's got these vertical electrodes. Again, that's a stack. In this case, it may look like 3, but it's actually 6 electrode couples, kind of left and right of each of the negative electrodes into the cell. So compared to the horizontal configuration where there's 1 electrode couple, this has now 6 times that. It's higher, it's better when you're packing cells together into systems because taller cells are more efficient, more efficiently use space. And these are large lunchbox size containers. Another question that we maybe got earlier on was, why aren't we just building one massive battery, one huge battery connect to the grid, like an aluminum smelter? And one of the reasons is that in order to efficiently connect to the grid, you need to get to the right voltage, about 1,000 volts. Each of these cells is about 1 volt. So you need to put about 1,000 of them together in series to get to 1,000 volts to connect to commercial inverters to convert your DC battery signal to an AC signal for the grid. And so that means that we don't want to build 1,000 swimming pool sized batteries as our first product. building smaller lunchbox size cells is easier, and you can produce them and get repeatability down and then build systems that you can then ship and deploy. Yeah.
What's the energy capacity of that size battery?
So cells like this will get to about a kilowatt hour of capacity. But we're on a roadmap to get there. We're at about half of that now, and we'll get to that over the next 2 years. Yeah.
Does that like modular design approach, does a lot of material go into like insulation for each of the?
Well, let me get to that in a couple slides when I have an image that helps with that. Yeah. Any questions? More questions? So as I asked earlier, what's the efficiency of the battery? So we've shown cells and operate cells at 80 to 90% efficiency. Was there a question online?
I have just one. The calcium electrode is solid, right?
No, it's a liquid alloy at our operating temperature.
Okay, but which one? The solid electrode is
the antimony. Yeah.
Doesn't that need to be replaced eventually?
So fair question. And we were hesitant to move to a system that had solid components in it because we were worried those particles would crack and degrade and fall off of the current collector. That ended up not being the case. That the negative electrode, because the antimony itself is conductive, as long as it kind of bumps into other antimony particles that are also have bumped into the current collector, that you maintain electrical conductivity to all those discrete particles. And so even if those particles fracture and break, we found we don't lose capacity in the system, that you can retain capacity with the solid particle electrode. So no, we don't have to replace the antimony. It's part of the battery that lasts for those thousands of cycles.
Okay, thanks.
Yeah, thanks for the question. All right, so the cells show 80, 90% efficiency, round trip DC efficiency. We've confirmed this with third-party testing last year and continue to do more safety testing and confirmation testing. This is a graph on the left showing voltage profiles of our cells under what's called C-rate operations, which is a weird thing that battery scientists use. C/4 means it discharges in 4 hours. C/10 means it discharges in 10 hours. And I don't know why they adopted this nomenclature. But you can see here the C/4 batteries, red lines are furthest apart. This is the most overpotential. So the charge and discharge voltage profiles are separated the most. And then the 10-hour and 20 hours are closest, because as we go discharge more slowly, there's less voltage drop in the battery. So the round trip efficiency goes up. So it's easy to go slower in our battery and most batteries. And then as we go faster and faster, the efficiency starts dropping off. So the main reason we're not looking at 1 hour or 2 hour applications is because then the efficiency starts getting worse and worse. And then here's some accelerated cycle life testing up to close to 5,000 cycles here, showing no capacity fade over this period. And we're targeting a 5% fade over 20 years of daily cycling. Safety is a very important issue. Lithium-ion batteries are the most widely deployed battery today. They have safety challenges. They're not showstoppers, at least not today. But there have been multiple fires and battery issues at some of the world's largest lithium-ion battery facilities, which has caused them to shut down and cease operation, and that's a huge impact. And so we believe our batteries are safer, despite being high temperature, despite having molten salt and reactive metals. Our batteries have significant safety advantages. If you short circuit our battery, it just discharges. It doesn't kind of cause any safety event. Crushing the batteries are in a thick stainless steel container, so that's very hard to do. Overcharging the battery and over discharging also doesn't create any safety event. In many batteries, if you overcharge them, you'll decompose the electrolyte, produce a gas, and that gas builds up pressure inside that cell, and then that can explode. And in many cases, that gas and the electrolyte is flammable, like in lithium-ion batteries, and then that electrolyte is what's actually catching fire, not even the electrodes in the battery. So our battery is immune to all of those safety issues. We've passed UL 1973 testing, which is a standard safety certification testing, which included shorting, high temperature excursions, voltage floating, Transporting the batteries is trivial. The batteries at room temperature are solid blocks of metal and salt. They can't pass electrons. There's no voltage, so there's no electrical safety hazard. And again, no flammable electrolyte to worry about. And so we've gotten authorization to ship our batteries around as well. Right now we are recycling our batteries, which is great. So as we're going through the development cycle, we build and test batteries, and then at the end of their life, we'll cut them open and analyze them. We can take those batteries, dunk them in baths of water, pull off a bit of hydrogen that forms from the calcium, and that gets vented at the roof. Salt dissolves in. You can then pull up the stainless steel, recycle it. Right now we're disposing of the antimony, but longer term we'll collect that as well and recycle that. And our goal is to minimize or eliminate all landfill waste. All right, so I've talked a lot about the cell technology. The product itself is not a cell. The cell operates at 500 degrees Celsius. No one's just going to buy a cell. You need to put a whole system together, which a customer can deploy. And so that happens by taking these cells, stringing those cells together onto trays. Those trays get loaded into a frame system, and that frame is placed inside of a shipping container, 10-foot shipping container. We then place about 6 inches of insulation between the inner or the outer wall of the frame and the inner wall of the container. And then that's the thermal insulation that's needed to keep the battery hot. We often get asked, well, don't we need to put a lot of energy into the battery to keep it hot? And the answer is, well, we do ship the systems cold. So we have electric heaters in the battery that we do need to power when we first install the system. When we bring the system up to its operating temperature, as the battery charges and discharges, it's not 100% efficient. It's 80, 90% efficient. So that loss of efficiency, that 10 to 20% of the capacity of the battery, is released internally as heat every time the battery operates. And that's all the heat that we need to keep that system at its operating temperature. And so once the battery is running, we don't have any kind of parasitic loss for heating or for cooling, really. We do have a small blower that can push ambient air through the system if we do need to cool it. Fortunately, it's really easy to cool something that's at 500 degrees Celsius, so that takes next to no energy. So we do couple these cells together to get to the voltage that we need. We insulate that container. The outside of that container is near ambient temperature. It's self-heated as long as it's operated once every couple of days. Our battery is not well suited for backup power applications. If all you want to do is have a backup system that is used once a month or once a year, not for us. But fortunately, what the grid needs for integrating renewables, which is the largest area of demand, is daily cycling needs. The system is modular, so we're going to have many of these 10-foot containers strung together. No moving parts on the cells, no pumping fluids. These cells are fully sealed and stationary, and scalable based on our materials, and can operate in hot climates or cold climates because of how well insulated it is. These cell systems will then go into larger deployments like this energy block of 32 megawatt hours of capacity. I guess for some additional context, one of these systems will get to about a megawatt hour of capacity. Well, what is a megawatt hour? A megawatt hour is enough to power about 100 homes if it's coupled with wind or solar. An average home consumes 20 to 30 kilowatt hours of energy a day. If you're getting half or 2/3 of it from solar or wind during the day, and the battery can then provide the other 10 kilowatt hours. So that's about 100 homes with a container like this. And so this 32 megawatt hour block would be 3,200 homes. They're 3,200 homes. And then you could string these power blocks together to gigawatt hour scale size systems, which is, I guess, the things have been covered by this, more than a gigawatt hour size system. And now the footprint of this system is actually quite competitive with best in class lithium ion systems. Which is another advantages of our technology compared to some other new technologies that are coming out. A lot of flow batteries, for example, might need 5 or 10 times the space than lithium ion. And so that might not matter at small scale demos, but when you're talking about huge gigawatt hour scale systems, it really matters. And we're fortunately quite competitive there. So, but really what matters at the end of the day is the cost of the deployed system. And we have several advantages there compared to lithium ion with lower capacity fade rate over a 20-year targeted lifespan. We're targeting 5%. I think we could actually do better than 5%, but we didn't want to assume 0% fade over 20 years. Lithium-ion degrades about 26% over a 20-year period. And so they actually need to oversize their systems and periodically augment those systems to keep the rated capacity of the system, because that's what we're paid to do. We also have a lower upfront capital cost of our system with lower end-of-line energy capacity, don't need to augment it as much for degradation and fade as mentioned. And the containers are relatively simple without needing HVAC systems and fire suppression and the same levels of safety that are needed for lithium ion due to the greater safety concerns. And then lower OpEx as well for service and warranty reasons. We really like what we're doing. We're excited about it. We think we're the best technology for this space across a number of different attributes, from low upfront system cost, low operating cost, very good cycle life, instant response time, which many batteries can do, but not all, reasonable efficiency, low footprint, no dependence on geological locations. There's some mechanical and thermal systems that do need large specific geographies rather. And then targeting this 4 to 12 hour application, which we think is the most important market for the energy storage and renewables integration. And so it's been fun as an organization to grow. And so we've been scaling up, and this is an image of our warehouse. These are barrels of salt that we order in by the tonnage, and scooping them out and drying them and processing them. And it has been fun to work with a team to build this out. Obviously, this work takes an enormous amount of effort by dozens and dozens of people, and team members have done a great job at getting us here. This is a cell assembly equipment on the far right here. Presently, we're in a prototype production facility. We would call R&D/prototype production. It's a manual process. We're moving our cells kind of manually, filling. There's some automation on the controls, but it's still very manual and laborious. What we're going to do with this next round of funding is pay for a high volume pilot facility, which will have high rate automated conveyance, robotic cell assembly and welding and joining equipment that will demonstrate that we can produce these batteries at high rates efficiently. And then we'll use that as a template to build a high volume facility for next year and scale from there. So such an interesting process, going from small R&D work to bigger cells, to then the equipment needed to build the cells, and then scaling that and going through all these different layers of scaling. As an image of our cell testing equipment, so we test 100% of our cells that we produce for quality check. We initially were using pottery kilns to test our batteries because they're cheap and easy to get. Unfortunately, they take a lot of space and they use a lot of energy. They're not designed to be very highly energy efficient, because when you're making pottery, you put pottery in, you close it up, you heat it up, and then you want it to cool down pretty fast, and then pull that pottery out and do it again. So so we had to design our own equipment. Now has cells side by side with some insulation between them, so they don't lose energy heat to each other during operation. So we use about 1/10 of the power and about 1/5 of the footprint with this equipment. So designing the equipment needed to build your equipment is part of the process here. Because we're in such a unique space, there's very little we can leverage from the outside world and existing industries. You can't just go buy the stuff off the shelf. You got to design it and engineer it and test it out and iterate on it, and you go from there. And so we've gone from developing and qualifying our initial commercial cells, building and qualifying our production and systems development equipment. This year, we're building up initial demonstration systems and developing our initial commercial systems, larger capacity systems. And then next year, we'll be launching a pilot manufacturing facility and producing commercial products out of that facility. And then again, the next year after this, building high volume facilities in 2024. So that was what I want to share today. It's been an exciting journey from the labs of MIT to where we are today, and still a lot of work in front of us to go to high volume production. But it's been quite the journey, and being a graduate student, working on a project the way we wanted to have an impact, I feel very fortunate to be kind of where we are today, and to proceed on that journey and get there. So we are designing these systems that have good high energy capacity, frequent daily cycling applications, long life, good efficiency, and we're thrilled to have fresh capital in the bank to allow us to expand our team, expand our facility, and accelerate our path towards helping us get to a cleaner energy future. So thank you for your time. Happy to answer more questions. I think there's still some time left.
Please ignore the poll just for taking attendance.
Okay. It's get in trouble if you don't come to the village. Any questions here or online?
Yes.
I have a question.
Yeah, go ahead.
So was there any consideration in potentially selling this technology to larger battery manufacturers, or has the goal always been to manufacture your own batteries?
Yeah, so we've gone through a torturous path on that topic. We started the company with the idea that we were going to do absolutely everything: the cells, the systems, manufacturing, the sales, the operation of our systems, the distribution, installation. Along the way, we maybe 3 years ago now, we actually pivoted to say, you know what, we really only want to focus on what's most critical for us, just the battery, just the cell technology, because we can leverage external outside groups. And so we actually signed a joint development agreement with a company called NEC Energy Solutions to develop the systems that our batteries would go into. So we would only be responsible for the cell, they would build a system, and we would sell them ourselves. We also had conceived of forming a manufacturing partnership, do contract manufacturing or joint venture perhaps, so that someone else would actually manufacture our battery. So we would really just focus on the design aspect of our cells. Two things that happened. One is that NEC Energy Solutions, their parent company, announced that they are winding NEC Energy Solutions down, which is so unfortunate because they were one of the top 3 global systems integrators, one of the largest integrators deploying lithium-ion batteries onto the grid. Another company called Fluence that hung around longer than NEC Energy Solutions, they just went public for, I think, $8 billion. And so maybe a missed opportunity there. So that impacted us. So we reassessed, we decided, you know what, we could get better margins, avoid margin stacking if we pull this work in-house. We'll need more capital to do that, but I think we can probably raise that. And so, let's do these systems engineering work ourselves. Then through the fundraising process last year, we had enough capital interest that the investors were saying, well, what would you do with more? And what would we do with more? I guess we would build our own manufacturing facility. So again, we can avoid margin stacking. And so we ended up going kind of back to close to where we started, which really depended on a few different external and internal factors.
Okay, 2 other students have questions. Sarah, please unmute yourself and ask your questions.
Okay, yeah, thank you. So my question, you answered a question about like why you don't do this for residential use, and that made sense. But I guess, are you considering it for industrial use cases? And the reason I ask is I know my spouse put in a foundry several years ago, and the cost to hook into the grid was such that they actually seriously planned and considered putting in their own natural gas generators to get the amount of power they needed to melt steel and iron. So is that a use case you're looking at too?
So there are behind the meter applications, typically called peak shaving. Often companies will get charged based on the peak amount of power that they use kind of at a very short window of time across maybe a month's time frame. And so there's some value there in having a battery that can shave that peak down if their load and demand is such that it's kind of very spiky usage. So yes, there are applications that are behind the meter, and we do need to be at the 1 to 10 megawatt hours, or I guess it's quarter of a megawatt hour to 2.5 megawatt hours of power needs for our batteries to make sense as a deployment. So it's not going to be as fit for a lot of applications behind the meter, but there certainly are applications like that.
Okay, thanks.
Yeah, thanks, Sarah.
Okay, any other questions?
Yep.
Sort of a follow-up on that. So it looks like you guys have like a modular on modular
approach. So I saw like you have the
Yep.
smaller cells and then a bigger encasing.
Yep.
So how much of the technology is like part of that bigger encasing? And could you make a smaller, like since your cells are compartmentalized, can you just make a smaller one of those
Like a container, smaller.
Yeah.
Yeah, so the question is, could we make a smaller container in different configuration? So for us, as we scale down our technology, we generate less energy per unit surface area. And so we end up needing thicker and thicker insulation. And so the economics kind of get worse because the capacity density and so forth get worse. So not ideal. We could scale down from where we are, but we think being in that shipping container size unit is really convenient for shipping and for installing systems. And that's how many battery systems are done around the world. So that was kind of our basis for actually defining our cell size. So we kind of started at the container and then said, well, within that container, if we want 1,000 cells, what sizes of the cells should we pursue? And so those factors kind of played into the size of the system that we ended up kind of proceeding with. Did I answer your question? Yep. Okay. Yep.
So pardon me if this is a dumb question because I have no background in batteries, but we've had a couple of presentations on batteries in the past, and in terms of demonstrating the reliability over long lifetimes, there's obviously the charge and discharge test. Something that I've always wondered is why can't, instead of charging up a whole megawatt battery and discharging it for one cycle, why can't you produce a the smallest possible unit that obviously would be less efficient but smaller, charge that and discharge it much more quickly and get some sort of efficiency from that, and then make a couple of sizes slightly higher than that, so you have some sort of calibration curve. Because then you could instead of extrapolating to 20,000 cycles, you could just test it with a smaller capacity.
Yeah, so for us, so we do test R&D cells, which are smaller, 4 inches by 4 inches, but 2 inches tall. And you're absolutely right. One way to accelerate cycle life testing is to, more specifically, thinning down the electrodes so that it takes less current times time or less capacity to fully charge and discharge. So you do that. You can end up getting into a regime where it doesn't make that much sense. So there's probably a limit as to how far you want to go there. But yes, you can shrink it down. But even with that, you're still going to be, an hour or even maybe half-hour charge, and it's still, still takes time to get to thousands of cycles.
Gotcha. Thank you.
Yeah.
And then one more trivial question is, if these units, they look like they're supposed to be placed outside typically, I guess that's probably because if they're giving off a ton of heat, you don't want them inside when trying to keep the inside buildings cool. Why don't you paint the whole thing green, or paint the roof with your logo, or put a little solar panel thing on the top or something people can buy?
There are more greener technology. I'm sure the marketing folks will have some say in that, but we're trying to focus on getting systems out the door, and so. But the exact configuration, there's opportunity to change that. And could you go with a custom sized container, and are the cost advantages there? Maybe it costs more to ship the systems if they're not kind of a nice shipping container size system. But those are all an important trade-off questions.
Or if it's going to go somewhere super cold, just like you have on the ground somehow.
We have conceived of, could you just stick these things on the ground and insulate it that way? Minimizing prep on site is critical for scaling and getting low cost systems deployed. Yeah.
If a battery like a container sized unit is finished its lifespan, what's the percentage of recyclable parts and material do you estimate?
Yeah, so the question was what portion of the system is recyclable? And so the main components in our battery are stainless steel, calcium, salt, and antimony. I guess insulation. And so we right now, again, are recycling our cells. And so we recycle all the stainless steel. That's pretty trivial to do by cutting the batteries open, dunking them in water, and salt dissolves away. And the calcium does react with the water, produce hydrogen, which bubbles off. So we don't get the calcium back, but we can get the stainless steel back. You get the antimony falls out, and that can be collected. We're not doing that today, but that is the plan. And then you have salt water left. The salt is so inexpensive. So calcium chloride is road salt. So that's what they spray, pour all over the road in the winters. And so it's very inexpensive and not really worth recycling. Maybe longer term we'll change our thoughts on that, but those are very easily recyclable.
There's another class waiting to get in, but so I think we're gonna have to end, thanks.
All right.
But, most people got the right answers in the poll, so molten salt is not corrosive.
Depending.
So,